This is section 5.5, trigonometric equations. It's the last section of this chapter. So here is a type of example you will see. It'll say something like solve sine of x is equal to the square root of 3 over 2. Well, we know that sine is positive in quadrant 1 and in quadrant 2, and that the associated ordered pairs in those quadrants are given here. So we could conclude that since sine is the y value, we could conclude that x is pi over 3 and 2 pi over 3. However, that's just one revolution of the unit circle. In fact, remember that sine extends forever and ever and ever. So the equation that we had before, sine of x is equal to the square root of 3 over 2. If we graph these, sine of x is in blue and the square root of 3 over 2 is in red. Really, anywhere there is an intersection is a solution. So there are actually infinitely many solutions to this equation. So the way we would write that is in this way. And let me kind of explain this to you. So if pi over 3 is here, then if I make one full revolution around the unit circle, I will get back to pi over 3. And one full revolution is 2 pi. If I make another one, I'm back. Another one, another one. So what this means is I can get back to pi over 3 with an infinite number of full revolutions around. And that's what this n represents. N is an integer. And remember, integers can be negative also, so I can go in the negative direction as well. So if I am asked to provide all of the solutions, I would have to write my solution like this and this. But oftentimes we're asked to just find the solutions between 0 and 2 pi. So this is what we're going to address throughout this section. Here is our first example. It says solve the equation on the interval 0 to 2 pi. So this is what you're currently familiar with, just solving it, an equation with one revolution. Okay, so let's just jump into solving this. Now looking at this, I see that it's the same trig function, which is great. It's cosecant throughout, which is helpful. So what I'm going to try to do is get the cosecants on one side by subtracting. So 3 cosecant minus 1 cosecant is 2, equal to 4. And I'm just going to isolate this cosecant by dividing by 2. So cosecant of x is equal to 2. Okay, now sometimes students struggle with cosecant, secant, cotangent. So what you can do is you can take the reciprocal of both sides. We know the reciprocal of cosecant is sine, and the reciprocal of 2 is a half. So we want to solve the equation sine of x is equal to a half. Okay, well, in this equation we see that sine is positive, and sine is positive in the first and second quadrant. And we know that sine is a half at multiples of pi over 6. So my reference angle is pi over 6. And what I need to do is identify which multiples of pi over 6 are in the first and second quadrant. So we will find that x is pi over 6 in the first quadrant, and it's not quite half a revolution, so it's not quite 6 pi over 6, so it is 5 pi over 6. Those are the two solutions within one revolution of the unit circle. Sometimes in this section you will see these answers written in this way as well. Okay, I'll accept either. Let's look at another example. Now, this one's a little bit different because it says solve the equation over the set of real numbers. So this means every single solution possible. So when we solve this, we're going to isolate the trig function. So we will subtract 5 from both sides. All right, divide by the square root of 2. Oops, this should be a negative 1. Oh boy. So cosine of x is equal to, when I rationalize this, I end up with a negative square root of 2 over 2. Okay, so we can see that cosine is negative in this case. And cosine is negative in the second and third quadrants. And we know that cosine of x is equal to the square root of 2 over 2 at multiples of pi over 4. So my reference angle is pi over 4. But now we need to figure out how we're going to write this. Well, the multiple of pi over 4 in the second quadrant is 3 pi over 4 because it's not quite 4 pi over 4. And just beyond that is 5 pi over 4. Okay, so these are going to be like kind of our foundation points. So if we want the set of all real numbers, let's first focus on x equals 3 pi over 4. Now, if I'm starting here and I make one full revolution around, that's adding 2 pi. If I make another full revolution, I'm adding another 2 pi, and another, and another, and another. And we can even subtract 2 pi. So we can say plus 2 pi n, where n is an integer. And I'll write that here in a minute. We also can do the same thing with 5 pi over 4. To get right back here, I'm just going to make a full revolution. So these are our two answers where n is an integer. You may see these answers written like this, which just says x in the set of all values where x is 3 pi over 4 plus 2 pi n and 5 pi over 4 plus 2 pi n. And then again, address where n is an integer. So that's the only difference. The other thing that you'll need to be careful of is this will be a little bit different when you're dealing with tangent and cotangent, and we'll address that here in a little bit. Okay, so in this example involves solving trig equations involving multiple or compound angles. So if you look at this equation, this one's a little bit different because the argument of the trig function is 2x rather than just x. So we will address how to solve that. So here, let's isolate the trig function. So I will add 5. Divide by 8. So cotangent of 2x is equal to 1. Okay, so we want to think about when cotangent is positive. Cotangent is positive in the first and third quadrants because both sine and cosine are positive here and both sine and cosine are negative here. Okay, so we need to figure out when cotangent is equal to 1. Well, our reference angle is pi over 4. So we need to figure out how we are going to address this. Well, I want to point out that if I start here in the first quadrant, if I add pi, I get to the other quadrant. If I add pi again, I get back. Add pi, plus pi, plus pi. So that means if I want to find all of these answers, now 2x in this case, would be equal to pi over 4 plus pi n, where n is an integer. Okay, now we want x by itself, so we want to divide everything by 2 or multiply by a half. So x is equal to pi over 8 plus pi over 2n. Okay, now this one's a little bit different because we want to figure out all of the solutions within this interval that can fit into this formula, if you will. So remember, n is kind of like a revolution, or in this case, half a revolution. So what I'm going to do is I'm going to plug in values for n, starting with 0, and then I'm going to end up with all of the values within this interval that fulfill this equation. So if n is 0, then x equals pi over 8 plus 0, which is pi over 8. Okay, well, perfect. That's our first solution. If n equals 1, then I have pi over 8 plus pi over 2 times 1. So you can get a common denominator. This pi over 2 can be written as let's see, 4 pi over 8, which gives us 5 pi over 8, still within one revolution. And we just keep trucking along here. N equals 2. So pi over 8 plus pi over 2 times 2. This gives us pi over 8 plus pi, which is 9 pi over 8. All right, well, that's just past half a revolution. N equals 3. Just keep trucking along. This gives us 13 pi over 8, which we can stop. And you'll see if you do plug in 4, you'll see that it's beyond 2 pi. So our solution here is pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. Let's look at some more examples of this type. Okay, so in this one, we want to solve the equation on one interval, but now I have a half angle. So the way we solve this is going to be very, very similar to the previous example. So we want to identify where cosine is positive. Cosine is positive in the first and fourth quadrant. And cosine is equal to root 3 over 2 at multiples of pi over 6. So my reference angle is going to be pi over 6. So when we are solving this, we have the following. Now I'm going to show you another way to solve this instead of using n. Okay, so either way is fine. All right, so we know that this is pi over 6 and this is 11 pi over 6. But the issue here is that we are dealing with x over 2 and not just x. So really, if we were just dealing with x, one full revolution would provide these two answers here. But because we're dividing by 2, we will likely have more answers than just this. So sometimes it's helpful to keep going. Okay, so if I add pi to pi over 6, I get 13 pi over 6. Oops. And you can keep going. All right. Now, in this case, I want x by itself, so I can multiply all of these by 2. And when I multiply everything by 2, I get x equals, this would be 2 pi over 6, 22 pi over 6, 26 pi over 6, so on and so forth. Well, reducing these gives me pi over 3, 11 pi over 3. Whoops, we might want to stop here because 11 pi over 3 is more than 2 pi. So really, I just have one solution here, which is this one. That's it. Let's look at more examples. Okay, so if the directions say find the general solution, that means find all of them. Okay, so that means we're going to have to add some multiple of pi. Okay, so here, looking at this, I know that we are dealing, so this is some angle, right? Call it theta. So if I have this, then I know that secant of theta is equal to 2. Well, again, sometimes this is tricky for students, so we can take the reciprocal. So cosine of theta is equal to 1/2. We know that cosine is positive in the first and fourth quadrants. And we also know that cosine is equal to 1/2 at multiples of pi over 3. So my reference angle is pi over 3. Okay, so in this case, these two multiples of pi over 3, those are going to be my foundations. So I'm going to start with this one. So pi over 3. Now, my theta is x minus pi over 4. Okay, so we're going to use that as my left side of the equation. So pi over 3 plus a revolution, like so. Okay, that's the first solution. But we're going to have to manipulate this a little bit. And the other solution is going to be the angle in the fourth quadrant. So x minus pi over 4 is equal to 5 pi over 3 plus 2 pi n. Okay, now if you struggled with that, pause it and come back to it. All right, now if I'm going to solve this, I want x by itself, so I'm going to add pi over 4. So x is 7 pi over 12 plus 2 pi n. Over here, add pi over 4. Get a common denominator, and you'll see that this is 23 pi over 12 plus 2 pi n. These two values of x represent all of the solutions, so we can write it in the following way. And make sure you say where n is an integer. Okay, let's look at another. Okay, so this is a higher degree trig function. As you can see, I have an exponent now. Okay, so I'm going to solve this in the same way. But I'll have to take the square root of both sides at some point as well. So let's add 1. And divide by 2. So I have cosine squared is equal to 1/2. Okay, well this is where I need to take the square root of both sides, and don't forget to include the plus or minus. So this becomes cosine of x is equal to plus or minus. Now when I take the square root of 1/2, I can take the square root of the top and the square root of the bottom and then rationalize. So this is really the square root of 2 over 2. Okay, well, I want to find out when cosine is positive and negative and equal to root 2 over 2. Well, that's all 4 quadrants, and it's multiples of pi over 4, so my reference angle is pi over 4. So I need to identify all multiples of pi over 4 within one revolution. And when I do, I get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And those are the solutions to this equation. Okay, so here is another higher order trig function that we need to solve. And we want all solutions between 0 and 2 pi. And I want to point out that often the left sign is a bracket, which means 0 is included and 2 pi is not. So sometimes you'll find that 0 is a solution and we don't want to include both of them, so we use an open bracket for the 2 pi. Okay, so in this case here, what we're going to do is we are going to compare this to just a regular quadratic equation that we have spent many years mathematically solving. So compare this to 2x squared plus 5x plus 3, where x is sine of x. Okay, so just keep that in the back of your mind for a moment. But if you were to solve this, you can solve it by using the quadratic formula or by factoring. And we are going to factor this. So remember, you want factors of 6 in this case, because you multiply these. Factors of 6 that combine to be 5, and both factors are positive. So this is how it would factor. Okay, so now that we know how to factor this, instead of x, we are going to replace x with sine of x. So this here factors into 2 sine of x plus 3 times sine of x plus 1. And just like we did previously, in other math classes, we will solve this using the zero product property as well, which means either this can be 0 or this can be 0. And if that's the case, then we'll solve each of these. So in the case here, I would subtract 3 and then divide by 2. So I would get sine of x is equal to -3/2. Well, in this case here, this equation produces no solution because sine must be between 0 and 1. I'm sorry, between -1 and 1. And in this case, it's not. So there's not going to be any solution produced here. So let's check the next equation. I would subtract 1 from both sides, and I would get sine of x is equal to -1. Well, if you refer to the unit circle, you'll find that sine of x is equal to -1 here, and only here, which is 3 pi over 2. This is the only solution to this equation. Now in this example, we're solving over the interval 0 to 2 pi. And I want you to notice that you have two different trig functions here, cosine and tangent. So that should be kind of a red flag, and you need to think about some different things that you can do with this. Now looking at these two terms, I see that there is a cosine in each of them, so I can factor out a GCF of cosine of x. When I do, I'm left with tangent squared of x minus 3 is equal to 0. Now some of you might be thinking, oh, tangent squared, I can use a Pythagorean identity. And you can, but it's not necessary here because all we're going to be doing is solving. And looking at this, I can set this equal to 0 and solve. And I can set this equal to 0 and solve. So let's do that now. If I set cosine of x equal to 0, cosine of x is equal to 0 here and here on the unit circle, which is at pi over 2 and 3 pi over 2. So there are two of the answers within this interval. Let's do the same thing by setting tangent squared minus 3 equal to 0. First, I'll add 3 to both sides. And then to eliminate the square, I need to take the square root, and I need to remember the plus or minus. So this gives me tangent of x is equal to plus or minus root 3. Okay, well, tangent is equal to positive and negative root 3 at multiples of pi over 3. And you should remember this before. And tangent, if we're dealing with tangent being positive and negative, that is all 4 quadrants. So we want all 4 multiples of pi over 3. So in this case, it'll be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So this one equation produces 6 solutions within this interval, and you will have to address all 6. Okay, here, if you look at this equation, you will see that you have sine squared and cosine. So you have two different trig functions. We can't factor this like we did in example 7 because if we were to factor this, we'd have 2 different values for x. So we can't factor. So instead, what we're going to do is we're going to use identities to solve this. And what I'm going to do, I notice that this can be replaced by a Pythagorean identity. So since I have cosine here, I'm going to replace sine squared with 1 minus cosine squared, minus 5 cos of x plus 5. If I distribute this 2, and combine like terms, and I would prefer to have my leading coefficient be positive, so I'm going to divide everything by a -1. And here I can see that now I have all the same trig functions. So I can think of this as 2x squared plus 5x minus 7, and I can factor that. So if I factor this, I get, so maybe pause it and see if you can do it, 2 cosine of x plus 7 times cosine of x minus 1. And then, like the previous problems, we will set each of these factors equal to 0. Now this one here, when you set this equal to 0, you get cosine of x is equal to -7/2. We can't have this. This is no solution. But this one, cosine of x minus 1, sure, cosine of x can equal 1, you betcha. That occurs at x equals, so cosine of x is 0 here, or I'm sorry, is 1 here, at 0, 2 pi, 4 pi, so on and so forth. But because of this interval, only 0 is included. And there's the solution. Okay, here we want to solve this. And looking at this, again, we have two different trig functions. We have sine and cosine. So let's see how we can address this. Now, oftentimes, we want one side of the equation to equal 0. So I'm going to, right now, subtract cosine of x. So this becomes sine of 2x minus cosine of x is equal to 0. Well, this is super messy. We don't like this so much. So what I'm going to do is I'm going to use a double angle formula and reduce sine of 2x to 2 sine of x cosine of x minus cosine of x. Okay, oftentimes if my argument is x, it makes things a little bit easier. Now looking at this, I still have two different trig functions, but I notice that in each of these two terms, I have a cosine, so I can factor out a GCF of cosine. And when I do, this makes it much easier to solve because there's one trig function here to solve and one here to solve. When I solve each of these, cosine of x is equal to 0. We've done this. Remember, cosine of x is equal to 0 here and here. So at pi over 2 and at 3 pi over 2. When I solve this other one, I'll add 1 and divide by 2. So sine of x is positive in the first and second quadrants with a reference angle of pi over 6. The reason I know that is because the ordered pair associated with pi over 6 is root 3 over 2, 1/2. Sine is the y value, so I know that my reference angle is pi over 6. The multiples of pi over 6 in the first quadrant and second quadrant are pi over 6 and 5 pi over 6. So there are 4 solutions in this problem. Okay, here is a problem. It's sine of x is equal to cosine of x. And I included this one because there are a few ways to solve this, but sometimes it's wise to work smarter, not harder. So let's just think through this for a moment. We want to know when sine of x is equal to cosine of x. So I could set this equal to 0 and manipulate it and solve, but let's just think about when sine of x and cosine of x are equal. Well, when does the same ordered pair occur? Because if the x and the y are the same, that means sine and cosine are the same. Well, that occurs at multiples of pi over 4, right? Because the ordered pair is root 2 over 2, root 2 over 2. So that is when sine and cosine are equal. But they have to have the same sign also. And cosine and sine have the same sign, S-I-G-N, in the first and third quadrant. So the multiples of pi over 4 in the first and third quadrant, pi over 4 and 5 pi over 4. Done. Now, I know there's not a lot of work here, but if you can show me this work, you can explain this work, this will absolutely suffice. Okay, let's look at this example. This one's a little bit longer, so just kind of bear with me here. Now, looking at this, in order to solve this, it's very complicated. I can't really do a lot with this so that I can get the same trig function. So what I'm going to do is I'm going to square both sides to produce something that's factorable. But if I apply a square to both sides, I must check for extraneous solutions. So that means like solutions that occur but really aren't solutions. Okay, so let's see what we can do here. I'm going to square this and this. And when I square the left-hand side, I really think it's helpful to write it down twice because you can't just distribute that square. So you have to FOIL this out, and when you FOIL it out, you get sine squared minus 2 sine plus 1 is equal to cosine squared. Okay, well, looking at this, I have different trig functions. Now, the left-hand side seems manageable, like I could maybe factor that, but I'm going to try to make this sine because I want the same trig function. So I'm going to apply a Pythagorean identity here. So I will get sine squared of x minus 2 sine of x plus 1 is equal to, this will become 1 minus sine squared of x. Okay, now let's get one side equal to 0. So I will add sine squared and subtract 1. So I get 2 sine squared of x minus 2 sine of x is equal to 0. There are a few options here. What I would probably do is factor out a GCF of 2 sine of x. So we're left with sine of x minus 1 equals 0. Okay, then we will solve each of these. In this case, I would divide everything by 2, and I find sine of x is equal to 0. sine of x is equal to 0 here and here. We want one full revolution, so we find that x is equal to 0 and pi. All right, let's solve this one. Sine of x is equal to 1. Sine of x is equal to 1 right here, which is at x equals pi over 2. So here we see that we have 3 possible solutions. However, since we have 3 possible solutions and we just randomly squared at the beginning of the problem, we need to check for extraneous solutions. So that's what I'm going to do on this next slide. I will remind you that we had the equation sine of x minus 1 is equal to cosine of x. And we found 3 possible solutions: x equals 0, x equals pi, and x equals pi over 2. So we're going to plug these values of x into this equation. When I do, sine of 0 is 0 minus 1 is equal to cosine of 0 is 1. Negative 1 does not equal 1. So I know that x equals 0 is not a solution. Now, had you put that in Alex, you would have been given that problem as being wrong, and you would have had to start over, which is not so much fun, is it? When I plug in pi, I get 0 minus 1 is equal to negative 1. Yes. When I plug in pi over 2, sine of pi over 2 is 1 minus 1 is equal to cosine of pi over 2 is 0. 0 does equal 0. Yes. So I have found that this equation has 2 solutions, pi over 2 and pi. Okay, here we want to solve this on the interval 0 to 2 pi. I can see that I have the same trig function, so I can factor this. I can think of this as 4x squared minus 7x plus 3 equals 0 and see if that can be factored. Turns out it can be factored, and it factors into 4 cosine of x minus 3 times cosine of x minus 1 is equal to 0. So I'll set each of these equal to 0 and solve. When I solve this one on the left-hand side, I end up with cosine of x is equal to 3/4. Now, cosine of x can be equal to 3/4, but 3/4 is not something on the unit circle. So what I need to do is I need to solve this by using inverse trig functions. So to get x by itself, I would take cos inverse of both sides, and I would find that x is equal to cos inverse of 3/4. And hopefully you thought, oh, I'm going to have to use my calculator. We will need to be in radian mode because I want my answers in radians. So this is going to be a little tricky, so I want you to just kind of bear with me here, okay? Now, cos is positive in these 2 quadrants, right? However, your calculator, cos inverse, will only give you one of these answers. Okay, we talked about cos inverse. It will only give you this answer in the first quadrant. So if you do that now in your calculator, you will find that x is approximately 0.7227. Okay, that is the first one. All right, well, if I want to find the second solution, this one right here, I use this kind of as a reference angle, right? So to get this, I need to take 2 pi minus the answer we just found. So, and x is equal to 2 pi minus whatever we just found, cos inverse of 3 pi, or 3/4, which is this value in red. And you will find that x is approximately 5.5605. Okay, so that's kind of tricky, but this is when you need to be smarter than your calculator. Okay, so this equation produces 2 solutions, but your calculator only provides one of the 2, so you have to find the other one. And then if we solve this second equation over here, cosine of x is equal to 1, cos of x is equal to 1 here, which in the interval we're interested in only occurs at x equals 0. If Alex wants you to provide the exact solution, you would say 0 cos inverse of 3/4 rather than the decimal. And you would also say 2 pi minus cos inverse of 3/4. Okay. Otherwise, providing the decimal of each of these would be just fine, which is this and this. In this example, we want to use a graphing utility to solve, because if you look at this equation, we have 2 cosine of x is equal to the natural log of x plus 3. That's pretty complicated to solve analytically. So what we're going to do is we are going to graph the first function in y1. And in y2, we will graph the second function. And remember, we are looking to find where these 2 lines intersect, and that will be the solution. Now, your graph might look different than the graph that I have provided. So what you can do to correct that is on your calculator, you can go to Window, Zoom, Trig. And that will give you a, the x-axis will be in radians, so multiples of pi. And so it'll be a little bit easier. Now you will absolutely want to calculate the intersection. You do not want to trace along until you get to the intersection. That's not going to work because that's going to be an approximated value, which is likely going to be incorrect. Instead, you want to calculate the intersection, which is right here, and it gives you this value for x. Remember, we want to solve for x to get the solution, which is right here. Now, so this is the answer. If you struggle with graphing on your calculator, please reach out to me and I can help you. This concludes the information from Chapter 5.